Okay. So we have two functions here, f of x and g of x. Okay. And so they intersect so that r is made up of g of x minus f of x here. So let me put this. So this is g of x is in green. What's in the chat? Okay, and then f of x is in blue. Okay, so we have two different regions to talk about here. The way to find the area in a region is to take the top function and subtract the lower function. So if I have two random functions and I want to find this area here, well, I need to take this top function, we'll call this f, and subtract this lower function from a to b. So if I wanted to find the area of this, it would need to be a to b f minus g. So that is how you find the area between two curves. And so it's kind of like the same thing, because normally we're trying to find the area between the curve and the x-axis. And that's just subtracting by 0 each time. So it kind of makes some conceptual sense, but let me know if this makes sense. Can I get like a 1 through 3 from both of you, where the area is between two curves is you subtract from, it's the top minus the bottom function. Thank you, Angelica. Thank you, Yasmin. Okay, so first thing first, we can't just subtract f and minus g, because for r, f is the bottom, but for s, f is the top. So what we have to do is we have to determine this point, and this is why it's a calculator problem. We have to set f and g equal to each other and put it into the graphing calculator. And I already have, hold on one second. I didn't have time to write this down, so I'm going to clear this. I've got the number here. It's 1.03 to, it's 1.033. So when you put this into the calculator, this point right here is 1.033. And so the first function, so the first integral for a, because we want to find the sum of regions R and S, g is the top function. So we do g of x minus f of x. And we're going from 0 to 1.033. And again, this 1.033 you get from putting both graphs in the calculator, and it will show this intersection. And then the second graph goes from 1.033 to x equals 2. Remember, we're differentiating with respect to x, so we don't care whether what the y value is. And from 1.033 to 2, f of x is actually the top function. Because remember, f of x is our blue here. So it's the bottom function for the first region, for R, and it's the top function for S. So R here, S here. So, and then when you put this into the actual calculator, I'll do R first. We can actually put the equation in. So we get g of x is equal to x to the fourth minus 6.5 x squared plus 6x plus 2. And of course, you subtract f of x, and I'm just going to put the f of x down. I'll fit it in. 1 plus x plus e to the x squared minus 2 of x. So you're just substituting in your g of x and f of x. And so for s, you're just doing the opposite, right? You're putting in f of x and then subtracting g of x. So you can actually put this into a calculator and it will do it for you. Now, which you're going to have to do because there's this x squared minus 2x is not going to really be easily solved with use substitution. So this is, like I said, this is a calculator problem. And so the answer you get is 0.997 from putting this in the calculator. So just to review, for this first region, R, G is the top function, and we're subtracting the bottom function F. And that's how we get region R, and it's going from 0 to 1.033 from the calculator right here. And so we can do the same thing for S. Because this is new material, I want to make sure you both are understanding. Can I get a 1 through 3 on how we solve for R? Because this is hard material, so. Let me know. You can privately message me. Oh, yeah. Okay, great. That's awesome, Angelica. Thank you. Oh, I didn't see you, Trayvon. My chat covers up the participants, so I don't see if someone joins in. Yasmin, Trayvon, is this making any sense? This is new material and it can be quite difficult, so let me know if Miss Rose is getting you guys calculators today. Is that correct?
Yes.
Okay, so, okay, no problem, Trayvon. Okay, so to solve for S, to kind of catch you up, Trayvon, how this works is we have two functions. We have a function f, which is in blue, and a function green, which is in green, or function g, which is in green. And so if we want to find the area R between two functions, well, we need to take the top function g minus the bottom function f from 0 to the intersection here, which when you put it in the calculator is 1.033. So we're just doing g of x minus f of x. Now to get s, now f of x is the top function. So f of x is the top function, so we're going to subtract g of x, the bottom function, from 1.033 to 2. And so we can put in f of x first. So f of x is 1 plus x plus e the x squared minus 2x. And then we subtract g, which is this whole x to the fourth. And this is a calculator problem, so you really want to do the do this on a calculator. And Rose is going to get you calculators today to help you practice. And so when you plug in this integral on your calculator, you get 1.0069. Okay. And so when it's asking for the sum of areas R and S. So R plus S, so R is 0.997 plus S. Oh, I know you can see switch screens. I didn't have that much time to prepare, so. And so I am switching to the answer key just because I haven't had a bunch of time to prepare and I don't have a graphing calculator on me, so I'm letting them do the calculator for me. And so that's the answer you'd get. Now the reason why we can't just do f minus g for the whole, from 0 to 2 is because f is the top for s, but it's the bottom for r. And so that's why we have to split it up. Can I get a 1 through 3 from you guys for just this part? I know it's some complicated numbers here, but okay, awesome. So, okay, good. I'm going to clear here. So, now we have region S is the base of a solid whose cross sections perpendicular to the x-axis are squares. Find the volume of this solid. So this is where it can get kind of difficult. So imagine we are taking the area, right? And we're approximating with rectangles, right? So we're taking f of x minus g of x, and we're trying to approximate with rectangles. Right? We're trying to do Riemann sums. But we want the exact approximation, right? So our rectangles are smaller and smaller and smaller until the width of each rectangle is basically nothing. They're just straight lines. Okay? So this is actually just the base. This is now a 3D object, right? So I'm no good at drawing, but we have this solid here, but it's got a height. And so these lines, the cross sections perpendicular to the x-axis, which these cross sections are perpendicular and they've got a height, are squares. So what do we know about squares? Squares have their two sides are equal, or actually all four sides are equal. And so if the bottom is the base, we know that this is f of x at the very bottom minus g of x. So just imagine the bottom of the square is standing up. The bottom of the square is f of x minus g of x. And if the bottom of the square is f of x minus g of x, that means the top of the square is f of x minus g of x. And so now we want to find the area of each square, okay? Because it's asking for the volume. But the way we do that is by adding up each area of each square, and so we can create the entire volume across the entire region. So to get the area of this square, it's just base times height. And so it's actually just f of x minus g of x squared. So in order to find the volume where all the cross sections are squares, so instead of adding rectangles, we are adding squares, where each side is the difference between f of x and g of x. This is very confusing, so please let me know. So remember, this point right here is 1.033 from the previous problem. So we're going to go from 1.033, where the solid starts, to 2. And we are going to take f of x minus g of x squared. Dx. If you manage to get this, you are golden. So please tell me if what I said the last 3 minutes makes any sense. Can I get a 1 through 3 from you guys? Because this is very difficult. So please, I wouldn't be surprised if I got some ones right now. Okay. Thank you, Yasmin. Thank you, Trayvon. Thank you, Angelica. Okay. So just to go over this one more time. Each of these lines here represents the base of a square. Because the cross sections of this solid, you can imagine there's a height involved that we don't see. We're just seeing the x and y plane, but there's a z-axis here. And considering the height of the z-axis is defined by a square, well, if the base of the square is f of x minus g of x, the height also has to be f of x minus g of x. Right? So this is the base. That is the bottom of the square. Imagine the square standing straight up. And the height is also going to be the same thing. And so now, in order to get the volume of the solid, we are adding squares. So we're adding all these areas, because the area of each square is f of x minus g of x squared. And that's why we put this in the integral to integrate from our first x value to our final one, which is 2. Does that clear it up a little bit more, Trayvon? Well, actually, no one was at a 3. So Angelica, Yasmin, does that clear it up a bit more? Okay, sweet. Okay, so now, if you get this, you can let the calculator do the work. Remember, we're only going for 1.033 because that's where the solid starts. And so you can put in f of x, which is 1. I appreciate you guys being brave and wanting to cover new material because this material can be difficult. Also, Ty, is it possible you can prepare another problem from this section? Just because I haven't had a chance to go through.
I haven't just been sitting here. I've been doing other stuff. But yes, I will do that. Yasmin, I'm going to send you a message, okay? If you could respond, that'd be awesome.
So that's f of x. We're going to subtract g of x here. I'm sorry about that. I wasn't sure if I was going to be going over slope fields or volume today, so because we didn't know how many people in class there would be, just because of the AP English exams. So I did f of x minus g of x, but this is all squared, right? Because we're doing squares. And when you plug this into your calculator, you get an answer. And the answer is 1.283. And that's part B. Okay. As I said, once you are able to get this integral, this becomes a lot easier. Okay. So we're ready to go on to part C. Luckily, C is a lot easier. Thank you, Mr. C, you're a lifesaver. Okay, we're going to do, for C, we got H. Let H be the vertical distance between graph and G in region S. Okay, well, that's simple. If H of X is the vertical difference between F and G in region S, well, okay. That's H of X is equal to F of X minus G of X. Find the rate at which H changes with respect to X when X equals 1.8. Okay, so all we have to do is find H prime and plug in 1.8. So we just have to take the derivative of H of X. And so we can plug in. So let's get H of X first. So first we have 1 plus X plus e to the x squared minus 2x, and then minus our g of x, which is x to the fourth, minus 6.5x squared plus 6x plus 2. And so you can take the derivative of this. Derivative of 1 is 0. Derivative of x is 1. Derivative of e to the x squared minus 2x is e to the x squared minus 2x times the derivative of the inside. Which derivative of the inside is 2x minus 2. And then subtract the derivative of g of x here, which is 4x cubed. minus 13x. Oh, plus 13x, I have to distribute. Remember to distribute the minus to everything. That's very easy to mess up. Plus 6. Remember, derivative of 2 is 0. So we get this derivative, and then all we have to do is plug in 1.8. And when we do that, we get negative 3.812. At least that one's a lot easier to plug into the calculator. Okay, so that is the entire question. It's new material, so I understand that it can be kind of difficult, and that's why I made sure to take a longer time on it. How do you guys feel on that, on this one? Can I get like a 1 through 3 from you guys on this one? Important thing to remember is that when you have two functions, in order to get area S, you have to take the top function blue and subtract the bottom one green. Okay, and that's the important info here. And for trying to do cross sections, well, they said this cross section's a square. So we had to take the square. Okay, well, the base of our square is a side. Our base of our square is each of these little lines here. It's f of x minus g of x. So we just have to square it to get each cross section. So they might give you semicircles, in which case you'd have to treat your base as 2r. And so you'd have to half it and then square it and multiply by pi. That's like another example, but just be wary of that. Are you ready, Mr. C? Or
yeah, give me 1 second.
Yep. Okay. Okay, I'm gonna clear.
Hi, everyone. Let's do this. Okay, so this is another example of this kind of thing. So we're going to let R be a region bounded by these two curves and the x-axis. So this whole area here. You're welcome. So we have two functions, y equals the natural log of x and y equals x minus 5. So which one of these is which? Well, x minus 5 is linear. That's this one, right? Also, natural log of x goes through 1, or the 0.10. So this one. So let me write that. Okay. And first, we want to find the area of the region R. So this whole bit here. There's a couple ways we could do this, but both of them are going to require us to have a little more information, right? So as we saw from Mr. Bay's example, like when you were subtracting the two functions and it looked something like one's over here and one's over here, we needed to know this point, right? Because we didn't know which one was on top. Like we need to know how to how to delineate when one's on top and when the other's on top. So this is kind of the same thing. So we need to know this point of intersection here. Because to find this area, right, we could kind of split this. Oh, that was a mistake. We could kind of split this wherever that is into two integrals to find the area. So the integral under this curve from 1 to whatever this x value is, plus the integral from whatever this x value is to 5 for this integral. Okay, is the goal clear enough? Can I get a yes or no? Yeah, cool. Okay, so my suggestion, this is calculator allowed. Graph these two functions in your calculator. So once you graph these functions, you can use a special feature of the calculator to find the intersection. But the first thing we need to do, again, is to find that point of intersection. Let's say the point of intersection, we'll call it A comma B, is it's about, yeah, I got it, thanks. It's about 3.693, comma 1.307. Okay. Now I'm looking at this, and there's a couple ways we could do this. I'm only going to show you one way because I think the other way is more confusing than it's worth. If you're absolutely interested, we can talk about it maybe some other time, but I don't know how much time we got. So if we want to find this area, the area under this curve, we could then write as the area of R is equal to, right, all this integral plus all this integral. So the integral from 1 to our x value here, the x value of our point of intersection, which is about 3.693. And remember, we're taking the integral under this curve because we're in this region, this part of the region R. So natural log x dx is what we want here. So far, this represents this part right here. We need to add, this yellow part here. Okay, so how do we do that? Well, we add the integral from, well, we start at the x value of the point of intersection, which is 3.693. And we go up until this x value here where it meets the x-axis, which is 1, 2, 3, 4, 5. And what's the function we're integrating under? Why, it's the y equals 5 minus x function. And again, this is the yellow region here. So we need to add these, right? Because, or we need to split this if we want to integrate it this way, because one function would continue over the other one here, and the other would continue over the other one here. So we can't just integrate under this curve, y equals natural log x, for this whole region, because it would be, you know, it would give us too much. It'd give us this extra bit here. Okay, that's your final answer for this part. You don't need to, I guess you could numerically solve it. Yeah, so yeah, you want to numerically solve it. This, when you put this into your calculator, yikes, okay, 2 minutes. When you put this into your calculator, you get about 2.986. So this is your answer for part A. And you'd get a point for your limits of integration, you get a point for your integrands, and you get a point for this final answer. Let's see if we can do B. Region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Write but do not evaluate an expression involving one or more integrals that gives the volume of the solid. So perpendicular to the x-axis, you can imagine I have these kind of squares here. I'm going to draw them kind of raised like that. That's terrible, but I hope you can kind of see what I'm getting at here. Maybe that's a little better. All right, pretend those are squares, okay? I'm trying to show the height a little bit. Okay, so we have infinitely many little squares there, and they're over here too, right? Okay, that first one's whack, but the other ones are okay. So how can we represent this as an integral? Well, or sorry, we're looking for a volume, right? Right, because we're looking for the volume of all these squares added together. Okay, and again, we know the area of a square. The area of a single square is whatever the side length is squared, right? So to find this entire volume, right, imagine all these infinitely many squares lined up next to each other, right? If we take the area of each of those and then add it together, we will get the volume. So we want the integral of all these square areas. I know we're out of time, but so the way that you can do this is the volume of, first we look at our first equation. We have the integral from 1 to our x coordinate of our, so the same interval as before. We are dealing with a side length of natural log x, but we want the areas, right? So we need to square the side length because the side length is given by the difference between natural log of x and 0. To finish this off, we need to add on the integral from our x point of our point of intersection to 5. Same deal for this one. Side length is given by 5 minus.
And ask them how it was going while you guys were finishing up your problem. But I had got kicked out of Zoom. Did you guys finish the last one or do they need to finish it?
I mean, I rushed part B and didn't get to part C, but.
Okay. What I can do is those who are on CalcMedic, you guys message me before you leave how it went and what's on. And then do you want to share, Mr. C? They have about 6 more minutes before the other one. Do you want to share and go through it?
Yeah, that'd be great. Just
Okay.
from the main room here?
Yeah, just from here. And I'm going to message the CalcMedic kids, the ones who are working on that.
Okay. So I know I went really fast. Yasmin, Trayvon, and Angelica, would you put a 1 through 3 just about this last bit here with the squares? Just so I know if I need to move this, keep talking about this. I'm happy to talk about this more, but we can move on if you're ready.
Edwin, Edgar, Adolfo, Sergio, this video will be on my YouTube, but this is new material, so don't worry about trying to get this right now.
2.9. Okay, great. I'm going to copy this picture because we have to deal with it again, and I've kind of marked it all up. Sorry about the sound. So for part C, we want to find the horizontal line y equals k that divides the region into 2 equal regions. We don't need to find this integral, but we want to find the value of k. Oh, I messed up. Sorry, technology. So this will be for part C. We need to find the value of k. Oh man, This one might be a little challenging. We need to find some value of k that splits this region in half. It'd probably be about, I don't know, there, right? So we need to find a y equals line though. So it is a horizontal line. So this would be our y equals k. And these two regions here are supposed to be equal when we find k. So our goal is to find k. So our goal is to find k. Well, our goal is to write an equation that could give us k. The tricky part with this one is, well, actually, sorry, give me a sec. Can we just do this with the x's?
I think you have to use y's here. I think you have to.
Yeah, I thought so too. I was trying to avoid that in the other ones, but okay. Yeah, so we need to use, yeah, it's way too complicated without it. So unfortunately, we need to integrate with respect to y. With respect to y. Why do we need to integrate with respect to y? Well, if we want to integrate with respect to x, just imagine the complicated nature of integrating this first part, right? We don't know this endpoint here because we don't know where k is. So you can imagine having a variable here. So we don't know that endpoint. We also don't know this endpoint here. We also have to deal with this split in the two different functions. This is a nightmare. But if we rewrite both our equations in terms of y, so y equals natural log of x, we can rewrite that by taking the e to the both sides. And then e to the natural log of x cancels out. So we're left with x equals e to the y. For the other one, it's a little easier. Y equals 5 minus x. If we add x to both sides and then subtract y to both sides, we get x equals 5 minus y. So now we have our equations in terms of y, or in terms of x. But we can write integrals now by kind of, instead of integrating under the curve like this way, we can integrate under the curve this way. Right? Because we have one function here and another function here. So if we take the integral this way, we've never seen this before, so I don't know if y'all are with me. If we
Instead
take
of finding the
area, then we can use this function and subtract it off from this function. So let me show you. Was there something you want to say, Mr. Bay?
Normally, we'd be trying to find the area above the x-axis. In this case, we're trying to find the area above the y-axis. But we're subtracting, to find the area, we need to subtract the two functions from each other to find the area between the curves.
Yeah, so now we're looking at y's. So if we're looking at y's, you can kind of imagine shifting your focus a little bit so that this is where, I don't know if it helps to think about rotating this. So like, if you have something like this, you kind of picture, I don't know if that helps. But the area under this curve, or rather between these two curves, we take the top one minus the bottom one. So this one's greater than this one in our x's. So we take this one minus this one. And remember, this one was 5 minus x, or rather x equals 5 minus y. And this one was x equals e to the y. So we need to take this right here. So that's why I've written it this way. This one is the more rightmost function. This is the more leftmost function. And what are our bounds? What are our limits of integration? Well, we need y values now in order to do this. Right, so 0 to whatever k is, right? So we don't know k, we want to find k. 0 to whatever k is will give us our bound here. Is this making any sense at all? Can I get a 1 through 3?
K is the point where if you have the line y equals k, it splits the area in two. So at the moment, we don't know what k is, but we did calculate the area from part B. So we do know what the area of the total shaded region is. And we don't have to solve this one. We just have to write the equation.
Right. Okay. So what is our goal again? Well, we want to find this horizontal line such that we split this region in half, right? But if you remember from the first part, we found the area of the region. So at this point, we can say, okay, this integral, we want it to be half of the area of the whole region, which we found in part A, which was 2.986. And this actually is your final answer, because we don't need to solve this. Okay. We don't need to solve this. So the difficulty here, in my opinion, besides all the new stuff, is yet another new thing, which we don't know. I don't know if we've seen integrating with respect to the y variable before, right? So just like with the x, where you look below a curve, y, you look kind of below a curve, except below is, we're looking horizontally instead. So below would be to the left of. Okay.
And again, for some of you guys, you're kind of just coming into this, so don't worry. I will have this posted by tonight, at the very least. Hopefully by this afternoon. But yeah, that's the entire problem.
Yep.
Okay, I'm gonna stop recording.